Good evening, statistics students. This is Mr. Marquetta, and I'm here to study Chapter 15 with you today. Before we start studying Chapter 15, there's a couple of important announcements I'd like to make about your exam. Your scores have been modified to include the curve we discussed in class. That was a 14-point curve on the multiple choice. Also, your points for Achieve have been entered into eCampus and are finalized, and also the Achieve Exam 2 Tech grade has been entered as well. So your exam number 2 is finalized. Tonight's lesson is about Chapter 15, Inference in Practice. And the homework associated with this is unlocked and available for you to complete until Monday night, November 15th. That being said, we are recording now. And if anybody in the class has a question they'd like to ask while we're in lecture, please feel free to unmute and to share what you think or to type something into the chat. Please be advised that if you do unmute, that you'll be part of our recording and that you'll be that the recording will be shared and other students will probably hear you. That's not a problem and you have no problem contributing. I'd love to hear what you have to say. Otherwise, you could say what you want to say in the chat and I can address it there and not mention your name. So that being said, let's start Chapter 15, which is about inference in practice. Today's objectives include conditions for inference in practice, how confidence intervals behave, how hypothesis tests behave, planning studies, and power. Let's start by talking about conditions and what conditions mean. Conditions for inference, in other words, the things that you need to be allowed to make inferences. Like you cannot look at your data and make statements or any kind of conjectures without certain specific things being in place. And if they're not in place, then your conjectures kind of have no foundation. So it is really crucial that you have certain specific conditions before you start making inferences. First, the data has to be a probability sample or come from something randomized. And when they say randomized, they mean fair and unbiased data collected from a sample that has been created such that it's really unbiased, different parts of the population, different sampling methods. Here we have statistical inference cannot remedy basic design flaws, such as voluntary response samples or uncontrolled experiments. If your data is not gathered appropriately, your conclusions may be challenged. So there is some leeway for error, but that error is not reserved for sampling errors. It's reserved for other errors. And the margin of error does not cover all errors. The margin of error is in a confidence interval covers only random sampling error. So it's important that we recognize that there is some leeway for error, but that error is specific to just variation, and we can't rely on that error when it comes to collecting our data correctly. So that's really important. That's one of the most important conditions for inference. And then here are some other examples of conditions for inference. We have undercoverage, non-response, and other forms of bias are often more serious than random sampling error anyway. So the margin of error does not take these into account at all. For instance, most opinion polls have a very high non-response rate, and that's not taken into account in the margin of error. So once again, sampling methods have to be in place so that you have an unbiased sample of your population when you're trying to do research. Okay, so let's talk about normality. It is also important that we have normality and all of the facets of normality, and we'll talk about that now. Sampling distribution has to be approximately normal. That is not true for all instances, but for the most part, it usually has to be normal. You have to be able to assume that the population that you are drawing from has normality, and it means that it has robustness, that it has a mean, and then standard deviations about the mean, with the right kind of data that makes it look kind of like a bell curve if you graphed it, whether it be as a histogram or something like that, that it would appear like a bell curve. Dot plots look like bell curves too that way. We're just assuming that they are, and there's not much else we could do. That's why it says, we rarely know the shape of the population distribution, so we have to rely on the sample data. When the data are chosen at random for a population, the shape of the sample data distribution should mirror the shape of the population distribution, meaning they should both be normal or both be bell curves. And we need that as a condition if we're going to start trying to make any kind of inferences, that we have a strong foundation in the fact that we have normal data and a normal population with a normal sample. So the other thing that is important when it comes to that normality is make sure you check for your outliers and see if there are outliers in the data that should be removed or should be modified because there are errors and things like that. All right. Now, let's talk about confidence intervals. We discussed estimating a population parameter and then having something of an interval around it that we could kind of give leeway of plus or minus so much and still be in the ballpark or in the area or the arena of what the number should be, basically. Confidence intervals are used in practice also for inferential statistics when they're doing research. Here we have confidence intervals are used to estimate a population parameter with a built-in estimate of the precision of that estimate. And the basic form of the confidence interval, if you recall, was an estimate plus or minus a margin of error. Confidence intervals rely on simple random sampling and the central limit theorem, i.e. on normality and on the whole concept associated with mirroring, how the population and the sample are mirroring each other that way. So remember that this is the formula for the margin of error, and it includes a z star that is associated with a specific confidence interval. And then we have the population standard deviation, which is sigma, and then underneath we have the square root of n. N is the number of trials or the number of items sampled or individuals sampled. If we decrease s, we decrease the margin of error, which means s, they're talking about the standard deviation. This is usually beyond our control, but sometimes we can improve our results by better measuring procedures. In other words, if we can get a better s, maybe we have a little bit of a chance of getting a better confidence. Also, if we decrease our confidence, we decrease the margin of error, and that goes vice versa as well. This trade-off is usually not useful, as lower confidence means less trustworthy conclusions. And we discussed if you have lower confidence, you have a little bit more of an interval, and vice versa. Then also, if we increase our sample size, and this is a very important part of today's lesson. If we increase our sample size, we decrease our margin of error. And unfortunately, that the presence of the square root symbol means that to cut our error in half requires a sample 4 times as large. What they're trying to say is, if you wanted to get more confidence, you would need to have more sampling, more people in the sample, or more of the items you selected from the population to study. And the fact that it's in the denominator in a square root, the fact that it's a square root only magnifies it and makes it that you need even more to get more confidence. So it's not like to get twice as much confidence, you would do twice as much sampling. You'd have to do something more like 4 times as much sampling to get half, as you could see. So it's like it's not a nice connection. It's like you really have to put a lot into it to get more confidence. So that's why when you see research done, that it's often a very large sample of people or of items that they're sampling. Okay, so for the same confidence level, narrower confidence intervals can be achieved by using larger sample sizes, and that's something we have to remember. Here are some examples of that, the effective sample size. If you look closely at these images, I'm going to zoom in so that we could get a good look at them together, okay? If you look at these images, first I want you to notice that this has a sample size of 5, and this one has a sample size of 100, okay? And if you'll notice, the red line is clearly very, very far away from the green line here. Whereas here, the red line is outside of the green line, but not quite as far away as it. That being said, let's take a look at the next case. And here we have another sample size that's different. We have a 20 versus a 250. So it's a very big increase and big difference. In the 20, you have one of them that's outside of the green. You see it's highlighted in red. But look over here, you have one of them also, and it's all the way up there. So these examples are here to help you see the idea of how the effect of the sample size can do something to the confidence. The fact that you're really far away in one situation implies that there's less confidence than in the other situation where you're even closer. That means that there's more confidence. The sample size is directly related in that way to the confidence. And in a backwards way, that's why you're in a position, if you use enough sampling, to be able to get the confidence that you were hoping to get. And that's something we talk about when we say the p-value and when we talk about hypothesis testing. Now, statistical significance only says whether the effect observed is likely to be due to chance alone because of random sampling. And I need you to remember that that's all the alpha is. That's all the test is. It's just the likelihood of it not being, the likelihood of it happening just to chance. And if that's very, very low, then that means that it happened for something other than just chance, which implies it might be my alternative hypothesis or the thing I'm trying to show, you know. So here are some ideas associated with that. Statistical significance doesn't tell us about the magnitude of the effect. So like if you see that you are statistically significant, but by a landslide, like not like your p-value is just under 0.05, but like 0.000 something, like so small that it was so clearly hit it out of the park, really significant. That doesn't necessarily mean that the hypothesis that you made, that you have for your alternative hypothesis is really, really, really true or truer than you think it is. It's just a matter of whether it passes or not. And the hypothesis still is kind of in concrete the way it's supposed to be. Also, statistical significance may not be practically important. In other words, it might not matter whether you have confidence about something or not. It might be true in another way that you don't even know. And also with a large sample size, even a small effect can be significant. And that's why the larger the sample size, the better off we are. So here's a case and how they would advise that you kind of begin to go about doing your work with the research for a situation. A drug to lower temperature is found to consistently lower a patient's temperature by 0.4 degrees Celsius, and the p-value being less than 0.01. That's very small for p-value. But clinical benefits of temperature reduction require a 1 degree Celsius decrease or greater. Plot your results and then compare them with a baseline or similar studies. So what they're saying is you would want to take your results from that specific study and try to connect it with a baseline or with something that's already been done before to see if you could get results for that. Okay. Now, sample size affects statistical significance. Like we said, the better the sample size, the better confidence we have, and then the significance is therefore impacted because of the confidence. Because large random samples have small chance of variation, very small population effects can be highly significant in the sample as large. In the same way, you could say that completely backwards by saying, because small random samples have a lot of chance variation, they have a great deal of variation. Even large population effects can be very, very insignificant or fail to be significant for the sample. So take, for example, instead of taking 1,000 people to study, you take like 3 people to study. If you take a very small amount of people and you have a very small random sample, there's a lot of chance variation in there. In other words, it's likely that they're very different than everybody else because there's only 3 of them. You know, like if you had 1,000 of them, then they would be all kind of a little bit better because you'd have more to kind of get together with the idea of the middle or the mean of it. You know, but if you only have 3, you know, you have a lot more variation in it. And in that situation, even large population effects can not even make an effect on what your data is with the samples if they're so small. So even more evidence that you really need to have a very large sample size when you're trying to do research. Okay, now this is interesting. Beware of multiple analyses. The probability of incorrectly rejecting HO, which is the type 1 error, and we're going to talk about type 1 and type 2 errors in a minute, is a significance level alpha. That thing that we were familiar with, because the confidence plus the alpha is 100%. Okay, so that 5%, that little chance that it's due to random variation and to random chance, that little chance of 5%, that is also called the type 1 error, and it's the probability of incorrectly rejecting HO. Now you want to reject HO, and you're hoping that whatever your research project is, that when you reject HO, you have evidence to support HA. But if you reject HO and you weren't supposed to, in other words, if HO had truth in it, then your research is flawed. And the point of it is that you're avoiding trying to make a type 1 error. That's a type 1 error, and it has to do with the confidence level that way. So the type 1 error is the alpha. Okay. So making multiple analyses, you can expect to make a type 1 error about 5% of the time. So if you do this 20 times, one of the times you're probably going to accidentally reject HO when you weren't supposed to. And it's kind of it's abstract to think of, but that's what 5% means. It means 1 out of 20. And if you keep doing the analysis over and over again, that idea is there, and you have to take it into account. So think of it this way: if you only run one analysis, it's not a problem. You probably won't be the 1 in 20, right? But if you try to run the same analysis with 100 random samples, you have to expect about 5 of them to be significant, even if HO is true, meaning that you had rejected HO incorrectly. So again, these are the ideas associated with inference in practice. And it's not exactly the kind of thing that you can go and do homework questions about, except conceptual ideas. So when you do your Achieve, you'll see that there's ideas like this in that, and it's really boils down to the best kind of research you could do, which is the highest sample size you can have, and with being able to have the right confidence to accurately reject HO when it's time to, because that's your end game. You run a test of hypotheses for extrasensory perception on an individual chosen at random. If you recall, that's what's ESP is short for extrasensory perception, meaning that you have an ability to read minds or something like that. So you run a test of hypotheses for ESP on an individual chosen at random. You then run the same test on 19 other individuals also chosen at random. What's wrong with that? Okay, so for a significance level of alpha equals 5%, you can expect that one individual will have a significant result just by chance, even if extrasensory perception doesn't exist. In other words, if you do this 20 times, 1 in the 20 is going to get it right. If you try to make them figure out what number you're thinking of, or hold up a card and ask them to figure out what they're thinking. There's a scene in Ghostbusters right in the beginning where the parapsychologist is Bill Murray, and he's doing that to someone, and he's trying to see if they have extrasensory perception by holding up a card to see if they can tell what the card is on the other side. The point of this is, if you're doing it with a 5% significance level, you can expect that 1 out of 20 people is going to kind of call the answers out right and appear to have ESP. Well, the reality is they don't have ESP and it doesn't exist, which is why you would say instead that it's a type 1 error, because you are rejecting the HO when you should not have. It just happened to come out that way because of every 5% is 1 out of every 20. So that's the concept associated with that one. Okay. So here's another case associated with multiple analyses. This one is about cell phones and brain cancer. Might the radiation from cell phones be harmful to users? Many studies have found little or no connection between using cell phones and various illnesses. Here is part of a news account from one study, and I'm going to read it, so try to follow along with me as I read it. A hospital study that compared brain cancer patients and similar patients without brain cancer found no statistically significant association between cell phone use and brain cancer, which is called glioma. But when 20 types of glioma were considered separately, an association was found between phone use and one rare form of glioma. Puzzlingly, however, this risk appeared to decrease rather than increase with greater cell phone usage. Interpretation. And then we have another one here, mammary artery ligation. Angina is the severe pain caused by inadequate blood supply to the heart. Perhaps we can relieve angina by tying off ligation, the mammary arteries, to force the body to develop other routes to supply blood to the heart. Patients reported a statistically significant reduction in angina pain. The problem? This experiment was uncontrolled, so the reduction in pain might be nothing more than a placebo effect. In fact, for this particular situation with angina, ligation has been discontinued, and surgeons no longer perform ligation because it has been shown that it is a placebo effect, that they feel better from it. And last, we have a randomized comparative experiment later found that ligation was no more effective than a placebo, and surgeons abandoned the procedure. Statistical significance says that something other than chance is at work, but it doesn't say what that something is. And that's, once again, another great example of how you can't take your findings and make it that they say something else. They're only there to just prove or disprove that HO. That's what that's really about. And you can't use it for anything else at all, including what it might have been, or what might be better than ligation, or why ligation might not have worked, or any of those things. So now we're going to talk about something a little bit more mathematical. This has to do with the sample size and how you can change the sample size based on the specific confidence that you're hoping for. We're also going to talk today about how to find power. Power is a measurement of how strong your study is, and it's also known as 1 minus beta. We're going to do that in a minute too. There's an applet that is on your eCampus Unit 3, Chapter 15 module. And that applet is called the power applet, and we're going to use that tonight to find power for a study. First, let's talk about how you would figure out what the new n would be based on whatever confidence you were looking for. Let's read, and then we'll explain the formula. You may need a certain margin of error. For example, a drug trial or manufacturing specifications. In many cases, the population variability is fixed, but we can choose the number of measurements. So, using simple algebra, you can find what sample size is needed to obtain a desired margin of error. Now, you remember learning about how the margin of error is m equals, and then you find z star in the table, and then you use the standard deviation from the population, and then you find the number of trials and put that in the bottom there. If you take that and solve that equation, m equals, etc. there, if you solve it for n, then you'll have what's on the other side of that arrow, which is n equals, and you'll have a new equation that is expressing everything in terms of all the other variables. So you have it as n equals. And in that case, you could plug things into this new formula to find out what your new sample size should be. If you want a certain specific confidence of 99%, go find the z star for 99%, put the standard deviation in there, put the margin of error in there, and then square it and figure it out, and that's how many you would need for a sample. So you'll see questions like this in the Chapter 15 Achieve problem sets, where they're asking you to determine what the best sample size would be. You come back to this slide in our lesson and make sure you look closely at this particular formula and use it to find the sample size. Okay. Here's an example. We're talking about density of bacteria in solution. A measuring equipment gives results that vary normally with a standard deviation of sigma equals 1 million bacteria per milliliter of fluid. How many measurements should you take to obtain a margin of error of at most 0.5 million bacteria per milliliter with a confidence level of 90%? So for a 90% confidence interval, remember that you can go to table C and you can look up Z star for that right at the bottom of the table. And we looked at that in the Chapter 4 PowerPoint. And for 90% confidence, the Z star figure is 1.645. Now we're going to use that figure along with the standard deviation, which is given as 1, as you can see there, and also with the margin of error m being 0.5. And if you look closely right there, I'm going to just illustrate it here while we're talking. If you look right here, you can plug all those things here. Here's Z star. Here's your standard deviation. Here's the margin of error that you're hoping for. And then you plug it in there and you square it and you get an answer. When you're done, the answer is 10.8241. What does that mean? That means that your sample size should be 10.8, but you can't do 10.8. So should you go with 10 or should you go with 11? Well, if you go with 10, you're going with lesser than the formula is requiring. So you have to go with more than it. Go to 11. The answer to this question is you should have 11. So just as a reminder, at the bottom of table C, I believe it's table C. Yeah, it's table C. At the bottom of table C, you'll see this little row here, which gives you all of the Z star figures for all the different confidence intervals. In this case, we used one for 90%, and again, it was 1.645. The summary of the exercise is using only 10 measurements will not be enough to ensure that M is no more than that. So therefore, we're going to use 11. Okay. Next, we're going to talk about something we like to call power, the power of a test. Okay. So the power of a test of hypothesis is its ability to detect a specified effect size and reject HO when a given HA is true at a significant level of alpha. The specified effect size is chosen to represent a biologically practically meaningful magnitude. So what affects power? The size of the specified effect, the significance level alpha, of course, the sample size n, of course, probably more than anything else, and the population variance, which is, remember, the standard deviation squared is the variance. So you can get that if you know one, you know the other. So now we're going to go through the exercise of finding a power calculation for a certain specific test. Here's an example of a test where we're researching, do poor mothers have smaller babies, which is a very ridiculous test. And as you can imagine, what does poor have to do with weight of a baby that's completely unconnected? So what we have is some data, and we kind of crunch it to find out what the power is, and you'll see the power is 80%, which is a smaller percentage than usual. Here we're going to talk about poor mothers and smaller babies. The national average birth weight is 120 ounces, and it's a normal distribution with the mu of the national average being 120 and the standard deviation being 24. We want to be able to detect an average birth weight of 114 ounces, 5% lower than the national average. What power would we get from a simple random sample of 100 babies born of poor mothers if we choose a significance level of 0.05? And the answer is 80%. Now, the reason why the answer is 80% is because if you look very closely here at the applet, we've inserted everything in there from the question. I have, and I'll point to it, I have the figure for the national population mean, and then I have indicating that it's less than, because remember it was 5% less than, so I'm using this one. We have it for a sample size of 100. Also, we're told the population standard deviation is 24. We're given an alpha straight out of 0.05. And then we're told that we did a sample, and then the mean was 114. We plug all of that in, and then the applet tells us that the power is 0.8. What I'd like to do with you now is actually open the applet and show you how you would input all that information to get the answer. So let's switch gears here. Okay, here we go. So let's go into our all right. Now right here I have the power applet. And then here in the power applet, I can put in everything I need. So here I'll put the mean, which was 120. And then I'll select mu is less than. And then I'll put in the standard deviation, which was 1 actually, wasn't it? Yeah, it was. And then I'll put in, no, the standard deviation was 24. It was 24. And n was 100 in the story. Alpha is at 0.05, but I could change it by going around like this. And then the alternate mu was 114. We say update. And if you look closer there, you'll see it says 0.804 right here. Okay, so that's how you can find your power using the applet. Okay, so now the next thing we're going to talk about, and this is really crucial, is type 1 error and type 2 error. Type 1 error, like we said, is alpha, and it's the accident that you would make if you were rejecting the null hypothesis, but you weren't supposed to. Type 2 error is when you fail to reject the null hypothesis, but the null hypothesis is actually false, which means, in other words, you do not reject the HO. And if you do not reject the HO, you're kind of implying that your hypothesis does not have anything to support it. There's no evidence to support the alternative hypothesis. So let's say that you accidentally failed to reject it because you were supposed to and you didn't. If you fail to reject it and it's actually false, that's a type 2 error. Now, type 2 error is also known as beta. In the same way that type 1 error is alpha, type 2 error is beta. And there's a connection between beta and power that we're going to talk about in a minute. But first, this is a really important part of this lesson, and I want you to try to remember these ideas and try to apply them to figure out when you have a type 1 error versus when you have a type 2 error. You'll notice that the correct decision is, in the case that HO is true, to fail to reject HO. That's what I'm looking at right here. Also, it would be great if I could reject HO because HA was true. Because if HA is true, that's what I'm trying to show. So the 2 stars I put in there are the two things I'm hoping for. What we don't want is type 1 error and type 2 error. And that would be the example that you reject when you weren't supposed to, or that you accept when you were supposed to, and vice versa. All right, so the probability of making a type 1 error is a significance level alpha. The probability of making a type 2 error is labeled as beta, and that's a Greek letter like alpha, it's beta. A computed value that depends on a number of factors, and the power of a test is defined as the value 1 minus beta. So in the case where we had a power of 0.80, beta was 0.20 in that case, and the probability of making a type 2 error was 20%, which is kind of high. The type 2 error is not definitive because failing to reject the null hypothesis does not imply that the null hypothesis is true. All that we're doing is we're just saying we didn't reject it when we were supposed to, not that it was true or not. So here's an example of a type 1 error. And for this example, we'll take a look at it and we'll think about it, and then we'll talk about what the answer is. A regulatory agency checks air quality for evidence of unsafe levels for greater than 5.0 ppt of nitrogen oxide, which is also known as NOx. The agency gathers NOx concentrations in an urban area on a random sample of 60 different days and calculates a test of significance to assess whether the mean level of NOx is greater than 5.0 ppt. A type 1 error here would be to believe that the population mean NOx level would exceed 5.0 when it really doesn't. That's what it would be, part B. And that would be because that would be when you would reject the null hypothesis when you weren't supposed to. That would be when it would exceed 5.0 ppt when it really doesn't. Okay. Okay, so that's what I've got for you guys. I'm going to stop our recording now. Thank you so much for your close attention to my lesson. If anyone has any questions about any of the ideas in this lesson, please feel free to email me with the class that I have here now. Thank you for paying close attention. I'm going to stop our recording now, and then I'll open up the floor to any questions. Thanks, everyone, and we'll talk soon.